On to round two, ladies and gentlemen. I'm going to let you know, in on a little secret, this problem. This is my second time recording this because the first time through it took me 5 minutes just to read through and get to part B. So we're going to do a little skimming. This exercise, unfortunately, is going to break down a little bit if you can't read and process and understand the problem in a timely manner. But I'm one of those people who likes to make sure I understand what's going on. So we're going to go over the 5 minutes here. The 5 minute timer is not going to necessarily be our golden rule, but I will let you know that the average score for this FRQ is about 5.5 points. So most people did not score a ton on it, which means there's probably a lot of blanks. We'll see how much we can get down for some setup, for some concepts, and make sure that we're putting in that effort to get us in a place where we can score some points without wasting a lot of time worrying about the hardest parts. So anyways, on to the problem. So it says a student makes a torsional pendulum by suspending a uniform disc of mass m and radius r on a light wire with a torsion constant kappa that is attached to the center of a disc as shown in figure 1. The rotational inertia of the disc is given by that. The student conducts an investigation to determine the relationship between the period of oscillation of the torsion pendulum and the number n of identical discs suspended from the wire. So it gets heavier. How does the time it takes to go back and forth respond? I'm going to guess that more discs, longer time. That seems like it would make sense. It says the student starts with a single disc, holding the disc at a small initial angular displacement theta naught from the untwisted position. The student releases the disc from rest and the pendulum oscillates. The student records the period of oscillation from a single disc. An additional identical disc is attached, and that becomes N2 all the way up to N10. First off, this is oscillations. However, we do not have a stock oscillation equation for non-uniform stuff, springs and pendulums. So it's all 100% internalized for this problem. They say using this equation, derive an expression for the period t as a function of n. Whew. Okay, well, first off, it's always important to take a look at what list of variables they want your answer to be in. By the way, minute and a half already passed. So capital T is equal to 2 pi square root of I over that k thing. I is the only variable that is in that function that they don't have listed there, but they got m's and r's. So it seems like the smartest thing to do is just take the rotational inertia and pop it in the formula and then move on and say we'll deal with that later. Except it has n there. You can have n times m because there's that many discs there, and that's done. We're done with part A. Part B, the potential energy stored in a torsional pendulum when the discs are displaced is this. On the following axes, sketch a graph for the maximum kinetic energy of the torsional pendulum. So with any sort of oscillator, the maximum U is going to be when the K is minimum, or technically when the K is 0, the U is going to be maximized. So the K maximum will be when it's basically gained all of the energy from potential. If you had like 100 joules of potential energy, your maximum kinetic would be 100. So if that's your max energy, then the K max is always just that value. That's not obvious. It's kind of a trick question, but it's the way it goes. Part C, they give us a graph and say, students plot t as a function of square root of n as shown. Cool. But that makes sense because up here in this equation, what we really have is t as a function of square root of n. So that's what they plotted. So we got that equation there. They plot it, and my favorite part of the whole FRQ here, draw a best fit line. Give me a point. +1, please. Or you do better than that. The students previously determined that the radius is 0.2 and kappa is that using the graph. Or anytime they give you set up a function and then they give you a linearized graph, in this case it is linearized, it's not just n, it's square root of n, they want you to find the slope. So we're not going to calculate that, but you can say that the slope is the delta t over the delta square root of n, and that can be calculated later. Stating you're going to find the slope, that's worth some credit right there. Then it says student finds that the values given from the manufacturer for the mass of the disc is less than the value determined. So if you calculated 1 kilogram here, it's listed as 0.8 or something. Determine a single source of experimental error that could result in the observed difference in M. There could be a ton of things. There's friction in the system, but that's more of just like a general error. Source of experimental error. So you could say that there's friction. You could say that the kappa is less than expected, because if the mass is supposed to be smaller and you measure it bigger, then that seems like there's more resistance to motion. So maybe the kappa is too weak. It could be any of those little things. You just make something up. Part D, if you make it to this part in the real FRQ, you'd just be skipping it. It says the student repeats the experiment, but now with discs that have a density that varies with the function of radius. Rho is equal to 0.3 r. Sweet. Love when they throw in volume densities into the problems. Would the slope of the best fit line of the new data be greater, less than, or the same? Well, this is the mass density. And the density goes up with radius. So it gets denser the farther out you go from the center. And the slope of the graph is dependent upon, we use the slope to figure out mass. So at this point, you can just make a best guess and say that because it's more dense farther out, that it's going to have a higher I value. So greater I, and rotational inertia, so slope bigger. This is not a high completion problem area, I don't think. And then part 2 of this, because, why not add a part 2 to it? When n equals 1, the maximum angular speed of the torsional pendulum with uniform disc is found to be WU, or omega sub u. When n is equal to 1, the maximum angular speed of the torsional pendulum with a non-uniform disc is omega sub non-u. Which of the following correctly compares those two? At this point, you could guess, I guess, if the non-uniform density has a greater rotational inertia, because as you go farther out, it's more dense, that it would be harder to rotate. So it should be quicker when you don't have the non-uniform disc. And for that, I'm not sure the best way to phrase it, but you can always throw in one of our favorite equations, work equals delta K, and just throw like an R there for rotational, because 1/2 I omega squared is what you get from whatever work's done. But that's kind of along the lines of what you'd put. But in this case, just writing these things it's probably a decent amount of points. And we spent about 7 minutes. So you got another 7 or 8 minutes in order to try to crank out some algebra on this right here to calculate the slope. But a lot of this problem is kind of proportionality conceptual. It's not necessarily doing all the number crunching. It's the what do you think would happen type problems, which are kind of annoying. But anyways, that's problem 2. We'll move on to problem 3.